Every propositional formula defines a truth function as follows. Suppose A is a propositional formula built from proposition symbols P1 to Pn. A defines the following truth function. F sub A with the arguments x1 to xn is the truth value of A under the valuation that gives Pi the value xi for I from 1 to n. This means that the value of the function f sub A at x1 to xn is the number 0 or 1 which we find in the truth table of the propositional formula A when we look at the row where P1 has value x1, P2 has value x2 and so forth, Pn has value xn. For example, if A is negation P1, then Fa, which in this case is f sub negation P1 at x1, is the truth value of negation P1 under the valuation which gives P1 value x1. So f sub negation P1 at x1 is 1 if x1 is 0 and 0 if x1 is 1. So this is the truth table of negation. Here is another example. F sub P1 conjunction P2 at x1, x2 is the truth value of the propositional formula P1 and P2 under the valuation fp1 equals x1 and fp2 equals x2. So f sub p1 and p2 at x1, x2 is 1 if x1 and x2 is 1 and 0 otherwise, as we know from the truth table of conjunction. Finally, let's look at f sub negation p1 or p2. This function at x1, x2 gets the value 0 if x1 equals 1 and x2 equals 0 and the value is 1 otherwise. This of course requires a little calculation. Whatever propositional formula A is given, we can quite easily define the truth function f sub A by simply building the truth table of A. This turns out to be a very useful method for creating truth functions. In fact, so useful that every truth function is of the form f sub A for some propositional formula A. We shall now indicate, without giving a rigorous proof, that every truth function is of the form f sub A for some propositional formula A. Let us look at the truth table of the truth function f and focus on the rows where f gets value 1. We simply forget the rows where f gets value 0. We represent f as the disjunction of those rows. There are 3 rows where f gets value 1. Let us call these the 1 rows. Now we use a trick. We know that a disjunction of several formulas has truth value 1 exactly when at least one of the formulas has. So we look for a disjunction of 3 formulas, because there are 3 ones, such that each disjunct picks exactly one of the 3 1 rows. We look for a propositional formula A, the truth table of which has 1 on exactly the same rows as f, that is, on the so-called 1 rows. We write A as a disjunction of three formulas because there are three ones in the truth table below A. The first disjunct is P0 and P1 and P2 because the first one row is a 1, 1, 1 row. The second disjunct is P0 and not P1 and P2 because the second one row in the truth table is a 1, 0, 1 row. The third and last disjunct is not P0 and P1 and not P2 because the third and last one row is a 0, 1, 0 row. This choice works wonderfully. Let us try. On the first one row of the truth table of F, we have x equals y equals z equals 1. This corresponds to the valuation Vp0 equals Vp1 equals Vp2 equals 1. With this valuation, the first top disjunct P0 and P1 and P2, and hence the whole disjunction A becomes true. What about the second one row? Here we have x equals z equals 1 and y equals 0. This corresponds to the valuation Vp0 equals Vp2 equals 1 and Vp1 equals 0. And, surprise, surprise, the second, that is the middle disjunct, is true with this valuation. Finally, the third one row likewise gives rise to a valuation which renders A true. But now comes the catch. What about the other rows? All those rows where F gets value 0. What happens to A on those rows? Let us assume we have a valuation which gives A the value 1. Then it gives value 1 to at least one disjunct. Say the last one, not P0 and P1 and not P2. Hence, the value of A equals 1 for the valuation which satisfies Vp0 equals Vp2 equals 0 and Vp1 equals 1. But this is the third one row of the truth table of F. Going through all the cases where Va can be 1, one can be convinced that indeed F equals f of A. In the special case that we start with a truth table which has no one rows, we simply let A to be the propositional formula P0 and not P0. This choice of A gives a truth table with all zeros. A side result of the trick we just learned for representing every truth function in the form f sub A is that every truth function can be defined by means of negation, conjunction, and disjunction. Namely, these are the only connectives that occur in the propositional formula A that we constructed. Thus, the set negation, conjunction, disjunction is a universal set of connectives. Even just negation and conjunction are, because disjunction can be defined in terms of them. Moreover, for every propositional formula A, we can form the truth function f sub A, and then for this f sub A we can find a propositional formula B as above by using just negation, conjunction, and disjunction with f sub A equals f sub B. So now A and B have the same truth table. We call such formulas logically equivalent. Thus, every propositional formula A can be expressed in a logically equivalent form, A1 or and so on, or AN, where each AI is of the form B1 and etc. and Bm, and each Bi is a proposition symbol or its negation. This is called a disjunctive normal form, denoted DNF of A. It is not at all unique. The one and the same A may have the same truth table with many different formulas that are all in disjunctive normal form. For example, a mechanically built disjunctive normal form of P0 arrow P1 could be the disjunction of three conjunctions. The first is P0 and P1. The second disjunct is not P0 and P1. And the third disjunct is not P0 and not P1. These three disjuncts correspond to the three rows in the truth table of implication, where implication gets truth value 1. However, this is not at all the simplest way to represent P0 arrow P1 in disjunctive normal form. Here is a much simpler one, not P0 or P1. Finding a disjunctive normal form for a propositional formula is an important tool for a better understanding of the formula. For example, seeing P0 arrow P1 in the form not P0 or P1 is often most useful. So this form, the disjunctive normal form, is worth keeping in mind.